Let's switch back to the document camera now and talk about two really important logic gates, which somebody was desperate to get to. So these gates are called Nand and NOR, and as you can see from the diagrams, they look a lot like and or, except that they've got the nose ring of contrarianism on the diagram and an extra N on the front of the name, and the extra N stands for negated. It is a negated and it's a negated NOR. And you have to be very careful. Whoever basically came up with these names was not being very careful, because it's tricky and you have to be precise and pause in all the right places to tell the difference between an AND gate and a NAND gate. You'd think that could go wrong very easily and achieve totally the opposite effect. Yeah, bad choice, but we're stuck with it. So remember, negated AND should be true exactly when AND is false. So first of all, let's figure out its truth table. Count to 3 in binary. Okay? So what's 0 and 0? 0, so NAND had better be 1. How about 0 and 1?
1.
Yeah, so 0 and 1 is also 0, so negating it should give us a 1. 1 and 0? 1 and 0 is 0. So don't shout what goes in the box. Answer the question I'm actually asking. Actually, that's a terribly important lesson for all of you. Lots of you don't read the question. And then you answer the question that you think it is, but that wasn't the question, so you get it wrong. Right? We have to be careful. We use language with precision. I asked for 1 and 0, and that is 0. So its negation is 1. What is 1 and 1? 1. So its negation is 0. Let's play the same game with NOR. So again, we're going to draw its truth table, so we should count to 3 in binary. Negated OR should be true exactly when OR is false. So 0 OR 0 is 0, so its negation is 1. 0 OR 1, 1, so its negation is 0. 1 OR 0, 1 OR 0 is 1, so its negation is 0. 1 OR 1, so its negation is 0. So if you think about what we're saying here, right? Negated OR, that's a knot of an OR, and De Morgan's rule tells us that's a pair of knots. And indeed, X nor Y is true only when both X and Y are false. So there's a connection with De Morgan's rules. Okay. Now, both of these gates have the property that they are universal. Let's figure out what that means. A universal gate is one that is enough, if you have as many copies of it as you like, to build all the digital circuits that are possible. So if we've got a large supply of NANDs, we don't need anything else. Similarly, if we have a large supply of NORs, we don't need anything else. It might be useful to see why that's true. It's also the case, by the way, that for gates with 2 inputs and 1 output, NAND and NOR are the only universal gates. It's useful to know that, and you should know that. I don't expect you to be able to prove that, but if you are interested in knowing why that's true, or even if you're not interested in knowing why that's true, I'll make a video about it. There's also some stuff in the teaching materials. Okay, so let me see if I can remember how to use this bit of the computer system that is where we're going next. So I built a little programming language for you to experiment with circuit designs. It's called CVI, and there's an introduction to it as part of your teaching materials. And you can just, well, it has rules. You can't just make anything up, and the rules are documented on the web page. So it's yet another formal textual notation that is supposed to be meaningful. And people complain about being made to use these things. I mean, you know, you turn up to a computer science degree and you complain about writing text that is supposed to have some kind of computational meaning. Great. Okay. So let's see how this works, how you build a component. The idea of this language is that you define kinds of component. I'm going to define not. So you start by putting the name of the thing at the top.
You start the cameras.
Sorry, yeah. You start by typing the name of the thing at the top, and then you specify the external connectivity. How many inputs has not? One. Okay, so it has one bit coming in, so you type a B, and you draw the outside of the box. The components are all boxes. Tell you what, actually, there's the key thing you've got to learn in CS 106 is that the world that we live in is made from boxes that are connected together with wires. Yeah? And what do you find if you look inside the boxes?
Wires.
You find more boxes connected together with wires. And the really clever bit is that some of the wires that are inside the boxes are connected to the wires outside the boxes. Good, isn't it? So we're going to explain how to build a new kind of a box. That's a not box, and it's going to have one wire coming in, which delivers a bit, and one wire coming out. That's somebody trying to invite me to a meeting, I suppose. What joy. And we need to explain how we're going to build a NOT gate. So what's inside the box goes between the two thick lines of equal signs. So you can see one wire coming into the box with a bit coming in, and one wire going out of the box at the bottom with a bit going out. And then in between the two, we've got to build the interior. So that our mission is to build these things using NAND gates. So we had the truth table a moment ago, and I can't show both annoyingly. But let's see if we can remember. Well, maybe I'll just switch back. It doesn't take that long to switch. Let's think about it for a moment. If you look at the truth table for NAND, and if you look in particular at the top row and the bottom row, you'll see that whenever we feed in 2 zeros, we get out a 1. And whenever we feed in 2 1s, we get out a 0. So whatever thing we want to negate, if we feed it to both inputs of NAND, the result will behave like a NOT gate. So let me draw that in ASCII art. You can draw it with a pencil sometimes. So I've got my vertical bar representing the wire coming in, and on the next line I'll use the the character, shift 6 on my keyboard, or hat, or whatever you want to call it, circumflex. It's not the circumflex accent in Unicode. So all that means is that one wire is being copied. I now have 2 wires that carry the same signal. So on to the next line, there are 2 wires coming in. Now I can put in a NAND gate. And to put in a NAND gate, I just type the name, NAND, inside square brackets. That's saying, I want a box here which is a NAND box. And then all I have to do is wire one wire of output from the NAND box to the output of the whole component, and I'm done. If I press send, something happens. So in this other box, in the tests box, I've written a bunch of test inputs that I want to feed to NOT. I want to see NOT 0 and NOT 1. And when I press send, out comes NOT 0 gives 1 and NOT 1 gives 0. Okay? Everybody cool so far? Right, let's just finish off quickly by building and OR. I'm just going to copy this chunk and paste it here just to have a little bit less typing to do. I'm going to change the name to and. And has 2 inputs. Now, how should we build it? We've got the ability to make a negated AND, yeah?
Should it be B and B?
The format for defining a new sort of box is that the name goes at the far left.
Alright.
So we are nonetheless saying that that the AND has 2 inputs.
Yeah.
So we're not giving the same syntax as in the formula, we're naming a new thing. So we're saying NOT is that picture. We're saying AND is this picture.
No, I mean like
yes.
When you've got the 2 inputs as B and B,
Well,
is that just simple, or should we put A and B or 2 different?
If you're writing a formula,
yeah,
you put the AND in the middle.
Yeah.
But when you're defining in this circuit language how to make AND in the first place,
yeah.
the name of the component always goes at the left-hand side of the line. So we're saying AND is this picture. We're
Right.
not making a formula that has an AND in it.
Okay, so it doesn't matter what letter you use.
Input labels.
So these inputs, they're labeled B because what's coming in are bits. B here stands for bits.
Right, okay.
We're saying there are 2 bits coming in. Later, you'll see H's coming in, which are hexadecimal.
Right.
So that's saying what the type of the thing is, what its external connectivity is. It expects 2 bits in, and we have, like, you know, when you have, let's see, here's an example here, right? This thing is a PowerPoint, and it's very carefully labeled with a diagram telling you what type of things it accepts. It's designed not to accept fingers or headphones. So it's important that when we're defining a new component, we explain what its connectivity is, how many inputs and outputs it has, and what sorts of things they are. Otherwise, we won't plug them together properly, we make terrible mistakes. Okay, so let's get on with it. We know how to make a negated AND, so how would we make AND?
Negate the NAND.
Yeah, negate the output, sort of flip it back over, right? That should give us back an AND. So we can wire the output of NAND into, and here's the good news, you could wire it into NOT, because we've already explained how to make NOT. And the rules of this game are, once you have explained how to make a component, you are allowed to use that component. So having explained how to make NOT from NAND, we are allowed to use NOT to make other stuff. And that's just good design. Okay, so if I press send, it confirms, yeah. So it says not is a box that takes 1 bit to 1 bit, and is a box that takes 2 bits to 1 bit. And I can feed in some test data. I'm going to want to run it on 0, 0, 0, 1, 1, 0, and 1, 1. And I press send. And out comes the result of our tests, which look a lot like the truth table for AND. Thank goodness for that. Let's think about how we might define OR using NAND. That also has 2 bits coming in and 1 bit going out. So how about this? Any suggestions? Yeah? You can do it with 2, but effectively that's what's going to happen, but it's how they're connected that matters. Remember, NAND means not both true, which is the same as one of them's false. And we want one of them's true, one of the inputs is true, so we can get that if we stick a NAND next to the output, but we negate both inputs. So instead of saying one of the inputs is false, we're saying one of the inputs is not false, which is the same as saying one of the inputs is true. I'll stick in some test data. And you can see that the test data indeed gives us the truth table for OR. So what you can see now is that you can build AND, OR, and NOT from NAND gates. And since you can represent all the logical formulae as disjunctive normal forms, that's to say built with OR, and NOT, that means you can build any circuit you need from AND, OR, and NOT gates. And as you can build AND, OR, and NOT gates from NAND, that means you can build everything out of NAND gates. And indeed, there are fabulous devices out there called FPGAs, field programmable gate arrays. And a field programmable gate array is just a lump of silicon covered in NAND gates. And all you do is you pre-program them by saying how the NAND gates are supposed to be connected up, and it becomes any silicon chip you want. So you can take an FPGA and turn it into whatever chip you want to do whatever kind of processing, just by wiring up the NAND gates into the appropriate circuit. Very handy things, often used for prototyping new pieces of hardware. FPGAs that are a wee bit slower than real chips, but they're good for prototyping. Anyway, it's 5:02, so I'll kick yous out. I hope that was okay. Could I have 1 minute papers in the box?